Section 11.5, and problems. So we're going to learn about probability problems that involve the word or, and also problems that involve the word and also mutually exclusive events and independent events. And we're going to do the problems in this section without constructing a sample space, so we won't be doing a tree diagram like we did in the last section. So or problems require to have obtaining a successful outcome for at least one of the given events. To determine the probability of event A or B, use this formula. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. If the probability of A and B equals 0.3, probability of A equals 0.7, and the probability of B equals 0.5, find the probability of A or B. So we know the formula, and we can go ahead and put in the values that we do know. So we know probability of A, probability of B, and probability of A and B, and we go ahead and simplify, and we come up with a probability of A or B equal to 0.9. Each of the numbers 1 through 10 is written on a separate piece of paper, and the papers are put in a hat, and one piece is randomly selected. Determine the probability that the piece of paper selected contains an even number or a number greater than 6. So we could construct a Venn diagram, and set A here shows the even numbers, set B here shows the numbers greater than 6, and we notice in the intersection of the two sets are the numbers that are both even and greater than 6. And we can find our probabilities now. The probability of being even, we notice there's 5 numbers in there, so that's 5 out of 10. The probability that the number is greater than 6, there's 4 numbers in set B. And the probability of being both even and greater than 6 is 2 out of 10. And we can go ahead and put those fractions into the formula, and we find the probability of selecting a number that was even or greater than 6 is 7 out of 10. And those numbers are 2, 4, 6, 7, 8, 9, and 10. Mutually exclusive means that two events are impossible to happen at the same time. We also sometimes call those disjoint. When they're mutually exclusive, then the probability of A and B is equal to 0, and the addition formula simplifies to, sorry, it wasn't on the screen there. It simplifies to probability of A plus probability of B. One card is selected from a standard deck of playing cards. Determine whether the following pairs of events are mutually exclusive, and then determine probability of A or B. So we have a deck of cards, and we're going to pick an ace, and we're also probability of picking an ace or a 9. It's impossible to select both at the same time, so the probability of an ace or a 9 is simply equal to the probability of an ace plus the probability of a 9. There's 4 aces in the deck, there's 4 9s in the deck, and so it comes out to be 8 over 52, which simplifies to 2 over 13. The probability of getting of A or B here is the probability of an ace or a heart. These are not mutually exclusive because there's an ace of hearts. So we have to subtract that probability of picking a card that's both an ace and a heart. And there's one card that fills that criteria. Excuse me. So there's 4 aces, 4 out of 32, 13 hearts, and then we have to subtract that event that occurs in both of those, one, which is the ace of hearts, 1 out of 52, and when we simplify, we get 16 over 52, and simplify that to 4 over 13. The probability of getting a red card or a black card. Impossible to select at the same time, so these are mutually exclusive events, so we have probability of red or black is simply the sum of their individual probabilities, and the probability of that happening is 1. The probability of getting a picture card or a red card. These are not mutually exclusive because there are red picture cards, and so we're going to go ahead and use our addition formula, 12 picture cards total out of the deck out of 52, 26 red cards, and then there are 6 red picture cards, so we have to subtract 6 over 52. We simplify that, we get 32 over 52, which simplifies to 8 out of 13. The manager at a local auto shop has found that the probability that a car brought into the shop requires an oil change is 0.61, the probability a car brought in requires a brake repair is 0.39, and the probability that a car requires both an oil change and brake repair is 0.19. For a car brought into the shop, determine the probability the car will require an oil change or a brake job. So we'll let event A be oil change and event B be a brake job. Notice that a car could require both of those, so they're not mutually exclusive. And we're going to use this formula. And we were given the probability of A, the probability of B, and the probability of A and B. And we go ahead and substitute those in, and we come up with the probability that a car needs an oil change or a brake repair of 0.81. And probability problems require that both of the outcomes have to have a favorable event. And we're going to use this formula. Probability of A and B is equal to probability of A times the probability of B. Since we multiply to find probability of A and B, this is usually referred to as the multiplication formula. The prior formula, the addition formula, probability of A or B, because we want to have at least one of those, we call that the addition formula. When we use the multiplication formula, we always assume event A has occurred when calculating the probability of B. So two cards are to be selected without replacement from a deck of cards. Determine the probability that 2 spades are selected. So the first time we go into the deck, there are 13 spades out of 52. Okay, we're not going to replace that first card, and we're going to assume that we got a spade. So on the second draw, we have 51 cards left to select from, but only 12 spades. So the probability of getting 2 spades is 13 over 52 times 12 over 51, which simplifies to 1 out of 17. Event A and event B are independent if the occurrence of either event in no way affects the probability of occurrence of the other event. Rolling dice and tossing coins are examples of independent events. 100 people attended a charity benefit to raise money for cancer research. 3 people in attendance will be selected at random without replacement, and each will get a door prize. Are the events of selecting 3 people who will be awarded the door prize independent or dependent events? They're dependent since each time we select a person, it changes the probability of the next person being selected because we don't put them back into the box for their name to be selected again. The probability the first person wins is 1 out of 100. We put that person's name aside. Then the second person we select has a probability of winning. On the second draw, it should be 1 out of 99. This should be person B here. 1 out of 99 and so forth. In general, any experiment in which 2 or more items are selected without replacement, the events will be dependent. And lastly, probability of an event happening at least once is going to be 1 minus the probability the event does not happen. If we draw 3 cards from a deck of 52, what is the probability we get at least 1 ace? So the probability of at least 1 ace is 1 minus, and notice that the event of at least 1 ace is the complement of the event of no aces. So the probability of getting no ace out of the deck, and think about this, the first time we go in, there are 48 cards that are not aces out of 52. We're not going to replace. The next time we go in, it's 47 out of 51 and 46 out of 50. And if you go ahead and multiply that out and simplify it, you come up with a probability of 0.217. Mr. and Mrs. Miller just moved into a new home and need to buy kitchen appliances. The chart below shows brands they are considering. Find the probability that they select GE for all 3 appliances, and then no GE, and then at least 1 GE. So GE for all 3 appliances. So the probability of getting a GE refrigerator, we notice there's 3 selections, and if we're going to pick GE, it's 1 out of 3, 1 out of 3, 1 out of 3, and that comes out to be 1 out of 27. The probability of no GE appliances. So in each category, there's 2 out of the 3 that are not GE, so we come up with 8 out of 27. Now, the probability of at least 1 GE appliance is 1 minus the probability of no GE appliances, which is what we just calculated in Part B. So we're simply going to subtract 1 minus 8 over 27 and get 19 over 27. Section 11.6 is conditional probability. And in this section, we're going to work on conditional probability, which is the probability of an event E2 occurring given that event E1 has already happened. And this is called a conditional probability. Remember that you're conditioning on the event that is to the right of that small vertical bar. And we read that as probability of event E2 given that event E1 has already occurred. A single card is selected from a deck of cards. Determine the probability it is a club given it is black. Okay, so the card is black, so there's 26 black cards in the deck, and 13 of those are clubs. So the probability of getting a club, given it's a black card, now notice what we're conditioning on becomes the denominator in the fraction, and then out of that denominator number, how many of those fit the criteria of the other event? And it's 1/2. A single card is selected from a deck of cards. Determine the probability it's black, given it was a club. Now this time there's 13 clubs, and they're all black. So the probability the card is black, given we know it was a club, has to be 1. For 2 events, E1 and E2, the conditional probability is determined by this formula. The number of events that fall into both E1 and E2 divided by the number of events in E1. And again, remember I said to you, whatever you're conditioning on becomes the denominator in the probability. 250 patients who had hip, knee, or heart surgery were asked whether they were satisfied, dissatisfied, or neutral regarding the results of their surgery. The responses are given on the table on the following slide. If one person from the 250 patients surveyed is selected at random, determine the probability that the person was satisfied with the results of their surgery. So we look at the table, there's 250 total, and how many were satisfied? 210. So this is going to be 210 over 250, which simplifies to 21 over 25. Now we're doing a conditional probability. Now we're going to just look at the people with knee surgery. There's 95 of those. How many of those were satisfied? We see 75. And then how about we're dissatisfied with the results given they had hip surgery? So now we've got 105 people with hip surgery, and 15 of those were dissatisfied. And then finally had heart surgery given they were dissatisfied. So 40 people were dissatisfied, and of those, 5 had heart surgery. A quality control inspector is checking a sample of light bulbs for defects. The table summarizes the results. If one of the light bulbs is selected at random, find the probability the light bulb is defective, given it's 20 watts. So we're only dealing with the 20-watt bulbs, and there were 100 of those. And how many are defective? 14. So the probability it's defective, given it was a 20-watt bulb, is 14 over 100, which is 0.14. Consider the figures below. What is the probability of selecting a purple figure given an even number was selected? So how many even numbers do we see? There's 3, 2, 4, and 6. And how many of those are purple? 2. So the probability of purple given an even number is 2 over 3. 2 dice are rolled one after another. Find the probability the sum on the dice is 10 given the first die is a 6. And you do have a handout in the Unit 4 module in my courses that shows the deck of cards and also the rolling the 2 die here. So how many outcomes have a sum of first of all, how many have it 6 first? So let's let the red die be the first die. So here's all the outcomes with a 6 first. And then how many of those have a sum of 10? And we see there's only 1, so this is 1 out of 6. Determine the probability the sum of the dots on the dice total 7 or 11, given the first die is a 5. So how many have a first die as a 5? We've got 6 of those. And then how many of those have a sum of 7 or 11? And there's going to be 2 of those. There's 1 and there's 2. So this is going to be 2 out of 6, 1/3 or 0.33. And the final section in probability is counting principle, and we're going to talk about the counting principle, and this as it relates really to what we learned in the tree diagrams. And we're not doing permutations. I should have left that out of there. If a first experiment can be performed in m distinct ways and a second in n ways, then the 2 experiments in that specific order can be performed in m times n ways. We already saw this in section 11.4. So Pizza House has 2 different salads, 6 different pizzas, and 3 different desserts. How many different 3-course meals can be ordered? We can use the counting principle. So the number of meals is simply salads times pizza times desserts, 36 different meals. Passwords. A password is used to gain access to a computer account and has to consist of 2 lowercase letters followed by 4 digits. Determining how many different passwords are possible if we're allowed to repeat first. Okay, so when we can repeat, we've got 2 lowercase letters, so that's 26 times 26, and then 4 digits, which is 10 times 10 times 10 times 10, and that comes out to be 6.76 million different passwords. Now let's change the criteria. Let's say we can't repeat. Now, if we can't repeat, we pick the first letter. We have 26 to choose from. We use that letter. We can't use it again. So in the second digit letter, we can only have 25 selections. And then we go to the first number. We have 10. We can't use that number again, 987. And now we're down to 3.276 million passwords. More restrictions. The first letter has to be a vowel, A-E-I-O-U, and the first digit cannot be a 0, and we can't repeat. Okay, so for the first position, we've got 5 choices. Now, once we've used that vowel, we can't use it again because we're not allowed to repeat. For the second digit, second letter, we have 25 to pick from. When we get to the first digit, we can't use a 0, so we have 9 numbers to pick from. When we go to the next number, we can use a 0, so we still have 9 choices, and then 8 and 7, and we come up with 567,000 different passwords. Here's another one we just did. This is the pizza time one. It's similar to the one I just did for you, 144 different meals that can be ordered. A multiple choice exam consists of 10 questions, each having 3 possible answers. And how many different ways are there to mark the answers? For each question, there's 3 possibilities, and there's 10 questions, so it's 3 to the 10, or 59,049 different ways. Lining up cars. In how many different ways can 7 different cars be arranged next to one another? So in the first position, we have 7, 6, 5, 4, 3, 2, 1, 5,040. This is actually called a factorial, and we put a little exclamation point as a shorthand notation to indicate that we're actually multiplying the number times 1 less, all the way down to 1. Consider the 5 letters A, B, C, D, E. In how many distinct ways can 3 letters be selected and arranged if repetition is not permitted? Okay, so for in the first position, we have 5 letters to choose from, then 4, and then 3, so we have 60 different arrangements that we can make.